Applications of the Fundamental Theorem of Arithmetic. Welcome, everyone. Let's begin our new session on the applications of the Fundamental Theorem of Arithmetic. Now, in our previous lessons, we established a very important foundation: the fact that every composite number can be uniquely expressed as a product of prime numbers. You might remember that this means no matter how you approach it, the prime building blocks of a number are always the same. Now you might be thinking, that sounds like a nice theoretical property, but how does it actually help me? Well, that is exactly what we are exploring today. The Fundamental Theorem of Arithmetic, or the FTA, isn't just a concept to memorize. It serves as an incredibly powerful tool for solving complex mathematical problems. The real magic happens when we realize that by analyzing the prime factors of a number, we can actually determine specific properties of that number, such as its divisibility or its ending digits, without ever having to calculate its actual, potentially massive, value. This is a shortcut that will save us a lot of heavy lifting in the slides to come. Determining numbers ending in zero. Now that we've established what the Fundamental Theorem of Arithmetic actually is, let's look at why it's so useful. One of the most common and practical applications of this theorem is that it allows us to determine whether a given number ends with the digit 0, without us ever having to actually calculate the full value of that number. Understanding the logic of numbers ending in 0. Now, before we jump into the calculations, let's take a step back and look at the underlying logic. To understand how the Fundamental Theorem of Arithmetic actually helps us solve these problems, we first need to understand the fundamental requirement for a number to end in 0. Think about it. A number ends with the digit 0 if, and only if, that number is divisible by 10. If we look at the number 10 itself and break it down into its most basic building blocks, its prime factorization, we see that 10 is simply 2 times 5. Now here is where the power of the theorem comes in. According to the Fundamental Theorem of Arithmetic, every number has a unique DNA made of prime factors. Therefore, for any number to be divisible by 10, its own prime factorization must, without exception, contain both the prime factor 2 and the prime factor 5. If even one of these two ingredients is missing, that number can never, ever end in a 0. The rule. Now, let's distill everything we've just discussed into a single, golden rule. Based on the logic we saw in the previous slide, that a number needs both 2 and 5 to create a 10, we can conclude that if a number's prime factorization lacks either the prime factor 2 or the prime factor 5, that number simply cannot end with the digit 0. It's a definitive test. If even one of those two essential ingredients is missing, the possibility of ending in 0 is completely ruled out. Detailed example, analyzing \4 and \. Now that we understand the logic behind why a number needs both a 2 and a 5 to end in 0, let's put this theory into practice with a classic problem. Let's examine whether the expression 4 to the power of n can ever end with the digit 0 for any natural number n. Now, you might be tempted to start calculating the values of 4 to the power of 1, 4 to the power of 2, 4 to the power of 3, and so on, hoping to find a pattern. However, we cannot simply calculate these values indefinitely, as they grow incredibly large very quickly. Instead, we are going to use the more efficient prime factorization method we just discussed to find our answer. Step 1. Analyze the base number. Now that we have set up our problem, let's move on to step 1, where we need to analyze the base number. Looking at our expression, the base is simply 4. To begin our investigation, we first need to find the prime factorization of 4. As you know, we are looking for the prime building blocks that make up this number. When we break it down, 4 is equal to 2 times 2, which we can write more concisely in exponential form as 2 to the power of 2. Step 2. Express the entire term in terms of primes. Now that we have identified the prime factorization of our base in the previous step, where we found that 4 equals 2 squared, we can move on to step 2. Our goal here is to express the entire term, 4 to the power of n, in terms of its prime components. Since we know that 4 is the same as 2 squared, we can rewrite the expression 4 to the power of n as 2 squared, all raised to the power of n. Now, applying our laws of exponents, specifically the power of a power rule, we multiply the exponents together. This simplifies our expression beautifully, transforming 4 to the power of n into 2 to the power of 2n. This step is crucial because it allows us to see the pure prime structure of the number, which we will analyze in the next slide. Step 3. Identify the prime factors. Now, let's take a close look at the expression we just derived, which is 2 raised to the power of 2n. By inspecting this expression, we can clearly see that the only prime factor present is the number 2. It is important to realize that no matter what natural number we choose to substitute for n, whether it is 1, 10, or even a million, the only prime factor present in our result will always be 2. There is no way for any other prime number to appear in this product. Step 4. Apply the fundamental theorem of arithmetic. Now, let's bring everything together using the core principle we've been discussing. The fundamental theorem of arithmetic tells us something very important. The prime factorization of any number is unique. This means there is one, and only one, specific recipe of prime numbers for any given value. Looking back at our work in the previous steps, we found that the prime factorization of 4 to the power of n consists solely of the prime number 2. Because this factorization is unique, it is impossible for a prime factor of 5 to suddenly appear. Since the prime factor 5 is completely absent from our expression, it is mathematically impossible for 4 to the power of n to be divisible by 10. Conclusion. So, to bring everything together, because we have clearly shown that the prime factor 5 is completely absent from the prime factorization of our expression, we can reach a definitive conclusion. The expression, 4 to the power of n, can never end with the digit 0 for any natural number n. We have moved from a complex-looking power to a simple truth about its prime components, proving that no matter how large n becomes, that essential ingredient of 5 will never appear. Real-world analogy, the recipe concept. Now, before we wrap up, I want to give you a way to visualize this concept so it really sticks in your memory. Let's step away from the numbers for a moment and use a real-world analogy. Think of prime factorization as a recipe. Imagine you are a baker, and your goal is to bake a very specific type of dessert called a zero-ending cake. To make this particular cake, the recipe strictly requires 2 essential ingredients, ingredient 2 and ingredient 5. If even one of these is missing, the cake simply won't turn out right. Now, let's look back at our mathematical problem from the previous slides. If we look at the recipe for 4 to the power of n, we find that it contains plenty of ingredient 2. In fact, it has quite a lot of it, but it completely lacks ingredient 5. There is no 5 to be found in that prime factorization. And here is where the fundamental theorem of arithmetic comes in to save the day. Because the theorem tells us that every prime factorization is unique, it means the recipe is fixed. You cannot suddenly find a 5 appearing out of nowhere just by increasing the power. Therefore, you can conclude with absolute certainty that you can never bake a zero-ending cake using the 4 to the power of n recipe. It's simply impossible because the essential ingredient is missing. Key takeaways. First, let's reinforce the rule for divisibility by 10. As we discussed when looking at the logic of numbers ending in 0, a number will only end with the digit 0 if its prime factorization contains both the prime factor 2 and the prime factor 5. If even one of those is missing, that 0 simply won't appear. Second, I want you to really focus on the role of the fundamental theorem of arithmetic. The most critical part of this theorem is the concept of uniqueness. Because prime factorization is unique, we can state with absolute certainty that if a prime factor, such as 5, is missing from the base of our expression, it will never suddenly appear in the final product, no matter how large the exponent becomes. As we saw in our example with 4 to the power of n, raising the number to a power only increases the number of 2's we have. It can never create a 5. Finally, consider the efficiency of this method. The beauty of using the fundamental theorem of arithmetic is that it allows us to analyze the properties of extremely large, complex numbers without ever having to perform the actual, exhausting multiplication. We can understand the very nature of a number just by looking at its prime building blocks. All right, let's wrap up our session by reviewing the key takeaways from today's lesson. Now, before we finish, let's look at a few common pitfalls to avoid in your upcoming assignments. Common mistakes. Now, before we wrap up today's lesson, I want to pause and address some common pitfalls. Even when you understand the logic, it is very easy to fall into certain traps during exams. Let's look at 3 specific mistakes to avoid. First, be careful not to assume that any even number ends in 0. I often see students think that because our example, 4 to the power of n, is an even number, meaning it is divisible by 2, that it might eventually end in a 0. But remember what we discussed earlier regarding the recipe for a 0-ending number. Being even is only half the requirement. To get that 0, you must also have 5 as a prime factor. Without the 5, the 0 simply won't appear. Second, do not ignore the uniqueness part of the fundamental theorem of arithmetic. A common misconception is the idea that if we raise a number to a very high power, say n, we might somehow create a new prime factor out of thin air. This is mathematically impossible. As we saw in our step-by-step analysis, raising a number to a power only increases the frequency of the prime factors already present. It never introduces a new prime factor like 5 into the mix. Finally, please ensure you distinguish between an exponent and simple multiplication. It is easy to confuse 4 to the power of n with 4 times n. If we were looking at 4 times n, the number could certainly end in 0. For instance, if n equals 5, then 4 times 5 equals 20. However, when we are dealing with the exponent, or 4 to the power of n, we must strictly follow the prime factorization rules we have just learned. Always keep a close eye on your notation to avoid this error.